So the inverse of Laplace transform is very simple. As we have different formulae, so inverse of Laplace transform, we can express this one is if the Laplace transform of a function, if a function ft is f of s, that is L f of t is equal to f of s, then f of t will be is called as the inverse Laplace transform. It is ILT. So this f of t is nothing but L inverse of f of s. L inverse of f of s. Then this L inverse is called as the Laplace transform in inverse. This is the Laplace transform. For example, that is L of t raised to the power n is factorial n. This is s n plus 1. Then L inverse factorial n s n plus 1. This is equal to Tn. So inverse of this formulation is the Laplace transform. The simple property, you can have one simple property, that is if f1s and f2s are Laplace transform of f1t and f2t respectively, then L inverse C1 f1s plus C2 f2s is nothing but this is C1 L inverse of L f of s and C2 L inverse of f2s. This is f1s. So these are the simple property, and similarly we can have other properties in the Laplace transform. Now for the sake of simplicity, we take some examples in order to explain the concept. So let us take the first example, that is the first example is the important example. The graph is shown as, there is t, here it is f of t, and this is 1, this is 2. So we can have this is this part is, so the function is a step function. The function is defined as the function is defined as f of t is equal to 0 when 0 to t is less than 1 and t minus 1 for 1 less than t is less than 2, and this is 1 for t is greater than 2. 2 is greater than 2. Solve it. Solve it means find the Laplace transform of the given function as shown in the diagram. This is 0, 0. So the Laplace transform, we know that the Laplace transform is expressed as L of f of t is equal to 0 to infinity e raised to the power minus st ft dt. So the function, we have three parts. First is 0 to 1, then 1 to 2, and then 2 to infinity. This is 2 to infinity. So first is 0 to 1, 0 to 1, e raised to the power minus st into 0 dt plus 1 to 2 e raised to the power st into, this is t minus 1 dt plus, this is 2 to infinity, 2 to infinity e raised to the power minus st into 1. This is dt. So this multiply 0 is 0 plus this is e raised to the power minus s into t and then 1 minus 1. So we have e raised to the power minus st minus 1 s. Minus s is uh, this is for this case, that is 2 to infinity plus 0 to 1 e raised to the power minus st into t, that is we can have e raised to the power x plus 1 x dx, t minus 1 is x, putting, so dt is equal to dx as a linear function. So what we'll have in case of this is minus 1 by s. Here it is 1 upon e raised to the power s infinity minus e raised to the power minus 2s, and this is plus e raised to the power minus s e raised to the power minus sx minus s into x 0 to 1 and 0 to 1 e raised to the power minus sx by s 1 dx. So this is 1 by s e raised to the power minus s 2. This kind here it is, this is 0. So we can have this kind of the expression. This is 2s and this minus and this minus positive, plus e raised to the power minus s upon s, and into e raised to the power minus s plus e raised to the power minus s upon s, e raised to the power minus sx upon s 0 to 1. So this is nothing but 1 upon s square, that is taken out, e raised to the power minus s minus e raised to the power minus 2s, minus 2s. So this is the Laplace transform of the given function ft in the given part. This is answer. Now the second example is very important, and I hope all of you are very much the second example is very important, and I think you have well versed with this example, that is some application, the initial value problem using Laplace transform d2y by dx square plus 2 dy by dx plus 5y is equal to e raised to the power minus x sin x, where y0 is 0, y dash 0 is 1. Solution. Now, before going to solve these kind of equations, let us see the importance of this equation. The importance of this equation is, this is very important in the application part, that is, either you are facing this kind of the differential equation in simple harmonic motion, that is when you are having the pendulum, we are having the pendulum and shifting this kind of motion. So the simple condition is F proportional to y, displacement. Force is directly proportional to displacement. Now the force is the acceleration. Acceleration is force but mass proportional to y. This is force per unit mass, because F is equal to mf, ma. Sometimes we can say a, acceleration. The acceleration is d2y by dt square proportional to y, with minus because of the simple harmonic motion, SHM, in case of SHM. So this is nothing but d2y by dt square is equal to k y. K is constant of integration. And if you have some mass, force, force constant, say unit mass, or you can say unit or some mass you are giving. So this is K over. We can say this is d2y by dt square plus ky is equal to 0. Is equal to 0. What is this? This is the free oscillation. This is the free oscillation. Equation of free oscillation. But free oscillation means once it start up moving, then it will move continuously. It will move continuously for infinite time, but it is not happening. After some time, it will, the amplitude will stop. Means there is damping. There is damping. So the damping force is proportional to velocity. Damping force is proportional to velocity. If we include the damping force with the velocity, so what we find? The d2y by dt square plus ky, this is proportional to dy by dt. And damping in opposite direction. So with some constant d2y by dt square plus b dy by dt plus ky is equal to 0. Again, this one is the damped equation. Damped equation. And if you want to make continuous oscillation, then we have to apply the force. We have to apply the force so that it will maintain oscillation. Or this is damped oscillation and the forced oscillation. So apply some external force to the set. So this one is d2y by dt square plus b dy by dt plus ky is equal to some force F1, external force. So this kind of equation is maintained equation or forced equation, and the nature of this kind of equation we have used in various cases in physics. Now, if this kind of equation is there, then one of the representative of this initial value problem, this is known as initial value problem because the initial values are given. What is initial value? Y0 is equal to 0. Means at the time this t is equal to 0, displacement is equal to 0. No displacement at time. And the dy by d0, that is 1, that is velocity. Velocity at this moment, dy by dt is the velocity, and the velocity is 1. Unit velocity is there. So these two problems, initial conditions are given in the case of the equation. Simple harmonic motion, there are sometimes LCR equation, we will different, some galvanometer equation. So these kind of things are there in the physics. So if this kind of equation is there, then how to solve these equations in this case? So we have this conditions, and let us solve this equation, which is very important. That's why it is very important. So now let us start the solving, taking the Laplace transform of the given equation, that is this Laplace transform of d2y by dx square y plus 2 Laplace transform of dy by dx plus 5 Laplace transform of y is equal to Laplace transform of e raised to the power minus x sin x. So writing the Laplace transform, this Laplace transform is, here it is s square y0 bar and s y0 with the minus sign by the formulation, or plus 2, that is s of y bar 0 minus y0 directly using the formula, and this is 5 y bar, and this is 1 upon s minus 1, this is whole square minus 1. This is the sign formula, Laplace transform. So the direct application of Laplace transform, putting the initial condition, that is y0 is equal to 0, y bar 0 is equal to 1. So we'll get this one is, here it is s square y bar minus 1, y is equal to 0, plus 2 s y bar minus 0 plus 5 y bar is equal to 1 upon s minus 1 का whole square, that is s square plus 2s plus 2. This is 2 plus. So this can be expressed as, you are taking this y bar is common, so s square plus 2s plus 5, s square plus 2s plus 5 y bar minus 1 is equal to 1 s square plus 2s plus 2. So we can express this one as s square plus 2s plus 5 y bar is equal to, this minus is plus 1 plus 1 upon s square plus 2s plus 2, or this y bar is equal to, this is 1 upon s square plus 2s plus 5 plus, this is s square plus 2s plus 2 plus s square plus 2s plus 5. This is part. Now the next steps is very simple, and it is the by making the partial fraction technique. We have this y bar is equal to 1 by 3 1 upon s square 2s plus 2 minus s square plus 2s plus 5 plus 1 by 2 s square plus 2s plus 5. what we have are, this is 1 by 3, this is s square plus 1, sorry, plus 1 square minus 1 upon s plus 1 whole square plus 2 square plus 1 upon s plus 1 whole square plus 2 square. This is y bar. Now taking inverse Laplace transform, we have what we have. This is y of x is 1 by 3 e raised to the power minus x sin x minus 1 by 2 e raised to the power minus x sin 2x. Plus 1 by 2 e raised to the power x sin 2x. That is 1 by 3 e raised to the power minus x. If you are taking common, then this is sin x plus sin 2x. This one is the yx. Solution. Solution answer. Now, if you take the traditional path, that is you are taking trivial solution that y is equal to this much dy by dx and then d2y by dtx, and then you solve, then that will have a longer way to solve. So this problem, this way, the problem is solved in more easily using the Laplace transform in our cases. Now we can also have the very important equation, that is you have very much used to with this equation, and this equation is very important, and using Laplace transform, solve the LCR circuit. Solve the LCR circuit. Or you can solve LR circuit. And let us make this LR circuit. First LR and then LCR. So what is LR? This is L, this is R, here it is source, this part is there. The VL and this is VR, two potential difference across this L. The solution is using Kirchhoff voltage law, in the given circuit, that is, this is VL plus VR is equal to E. L is di by dt plus this VR, R into I is equal to E. R into I is equal to E. So this E can be expressed as E small e of at. By taking the initial condition, what is the initial condition? I at 0 is equal to 0. Now take the Laplace transform. Take the Laplace transform, that is L of this L into I dash t plus R L of I of t, that is E L of e raised to the power at. So this is nothing but L s into I s minus I 0 plus R I dash s plus E is equal to E s plus A. S plus A. So initial condition, that is I is equal to 0 at this point. So it is 0. L of S I plus plus R I is equal to E s plus A. So Is is taken out. Ls plus R is equal to I bar s is equal to E divided by s plus A. So this I bar s is equal to E s plus A. This is Ls plus R. Ls plus R. This can also be written as E using partial fraction s plus A 1 upon R plus Ls minus R plus Ls 1 upon S plus A. S plus. Taking inverse Laplace transform. What is this? This is the partial fraction. This is partial fraction. This is the partial fraction. Taking the partial fraction, that is IT L inverse IS is equal to E of this R plus Ls L inverse of 1 upon S plus A minus L inverse of 1 upon S R plus Ls. we can have this one is E upon R minus AL. How it is AL? That is S. For this S we have here R. And this is e raised to the power L inverse of 1 upon S plus A, that is e raised to the power minus 80. Here it is e raised to the power, you are taking S in place of S, this is R by L into T. R by L into T. Shifting of the part of the current. So this IT is E R minus AL e raised to the power 80 e raised to minus R by L of T. So this is the current. This is the current parameter. What is R? Where R by L, R, L by R is equal to tau, that is time constant. This is time constant. And we have to define the value, that is how much time constant is there, and this way. So on the use of this part, Laplace transform, we can solve the given equation in a very simple way. And the next part is that I have said we are adding all these three one. Next example, using Laplace transform, solve the Lcr circuit, that is L, C and R. LCR, using Lcr circuit. So solution, using Kirchhoff voltage law, the potential expression, is, this is E, this is VL, this VC, this VR is equal to N. So this is L di by dt plus 1 by C integral I dt plus Ri is equal to E. Initial condition, this 0 is equal to 0. Now taking constants like A is equal to R by 2L, omega square is equal to 1 by LC minus R square by 4L square, and K square is equal to minus omega square. Taking the constants, what kind of constant is in the various form? So taking Laplace transform, take LT of above equation, this is L, LS I plus R S 1 by CS IS is equal to E by S. So this is Lc s squared plus RCS plus 1. This is 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 equal to EC solving. So this IS current of this bar is EC divided by LCS square plus RCS plus 1. But taking simple, this one is LCM. So this is, if you take common L, E by L cancel C, then this is 1 upon S square plus R by L into S plus 1 by LC. 1 by LC is nothing but it is omega square. Omega square. So what we have, this is E by L. This is 1 upon S plus R by 2L square. So in this bracket, this is L R square upon 4L is the extra term if you are squaring over there. So you subtract it, plus 1 by LC minus R square upon 4L square. This part. R square by 4L square. So we can express this E by L 1 upon S plus A whole square plus omega square. Omega square is the frequency part, and S plus A, this is 2L, that is there, A, and here it is omega square. This is omega square. So what we find, we can have this IS. Now taking inverse of the Laplace transform, this is Laplace transform, taking inverse Laplace transform, that is IT is equal to L inverse IS is L inverse of E by L 1 upon S plus A whole square plus omega square of this. So IT is equal to E by L omega e raised to the power A into sine omega t. Sine omega t. This is the solution. Now analysis. First, if omega is equal to 0, so IS is equal to E by L 1 upon S plus A, then L IT is equal to L inverse of this E by L 1 upon S plus A whole square. So this it is equal to E by L e raised to the power at into t. This. Second, if omega square is less than 0 and omega square is equal to minus k square, negative. So I of this is E by L 1 upon s plus a whole square minus omega square or minus k square, that is E by L of 1 upon s plus a whole square minus k square. So taking inverse, it is equal to inverse of Laplace is inverse of this, that is E by Lk e raised to the power at into sine hyperbolic kt. So it is equal to e raised to the power e upon Lk e raised to the power minus at sine hyperbolic kt. This is the solution. So in this way, what we find that in a very simple way we can have the Lcr circuit, or we can discuss the circuit containing the Lcr and so on so forth. So advantage of this is we can solve the complex system in a simple way. Two examples which are asked in examinations are very important, and these are an infinitely long string having one end at x is equal to 0 is initially at the rest along x-axis. The end x is equal to 0 is given a transverse displacement ft. When t is greater than 0, find the displacement of any point of the string at any time. Solution. An infinitely long string has one. Suppose this is x is equal to 0 and here it is infinity. Infinitely long string having one end at x is equal to 0 is initially at rest. This is initially at rest. at end x is equal to 0 is given a transverse displacement. Here it is transverse displacement. This is f of t. F of t is transverse displacement, that is pulse. That is pulse. When t is greater than 0, t is greater than 0, this is x0, t is equal to 0. Initially rest first. Then at t is equal to greater than 0, there is a pulse. Pulse given. So what pulse is? Pulse is moving towards the infinity. So find the displacement at any point at the spring at any time t. Any time t. So this is the condition, and we have to find out a pulse displacement at this t is not equal to 0 sometime. We have to find out this case. So let yxt, this value is yxt, be the displacement, then wave equation is delta 2y by dx square is equal to c square d2y by dt square. Subject to condition, that is initial conditions are what conditions? Y x0 is equal to 0 and y0t is equal to ft. ft. So dy by dt is equal to x0 is equal to 0 and this is yxt is bounded. Is bounded. Is bounded. Taking the Laplace transform of the above equation, that is L of is equal to c square L delta square so this is s square y0 s y0 x using the formula on putting y x0 is 0 and del y by del t x0 is equal to 0, we get this term is 0. So s is square y bar is equal to c square. This part is 0 and this part is 0. Initially, two conditions are 0. So r d2y by dx square is equal to s by c whole square into y bar. Now, this is y0s is equal to, taking inverse, is f of s at x is equal to 0. On solving, we have y bar is equal to a e raised to the power x by c plus b e raised to the power minus x by c. Why? Because there are possibility to move forward as well as reverse direction. Now this part is 0 because when x tending to infinity, this factor is infinity. So y bar is b e raised to the minus x by c. E raised to c. Putting the value of y bar 0 s is equal to f of s at x is equal to 0, we get f bar s is equal to b constant. So y is after this, y is equal to f bar s e raised to the power s x by c. And this is 1 upon 2 pi I a I omega a plus I omega e raised to the power t x by c of s into fs ds. So this is f of t minus x by c y xt. Inverse law. So after this time, at any time, the pulse is t minus x by c, t minus x by c. So this is the solution, and this kind of solution we have in case of the discussion of wave equation. Wave equation, and that is over there. Now another equation. Another equation that is important, that is known as thermal equation. That is, if one end is heated with respect to other end, heat equation. The next important example is Example is, this is famous heat equation. It is very important, and severally you have seen your example. Heat equation means, suppose this is the material and this material is heated at this end. This is heat source, at high temperature. At this point x is equal to 0. Here it is x is equal to L. So we can take the segment, two segment. Here it is x plus delta x plus delta x. So this part is delta x. This part is delta x. The temperature is, this is the position theta, and theta minus d theta. Temperature is theta minus d theta is the initial, but here we write theta plus d theta, but there is a temperature gradient. There is a temperature gradient, and at that time we can have the equation. So the temperature gradient is d theta by dx, and delta theta is minus d theta by dx into del x. How much temperature is there? So at point C and D, the temperature is at point D, that is d by dx theta minus d theta by dx into this part. So this is d theta by dx minus d2 theta by dx square del x. Let theta 1 and theta 2 be the rate of heat flow from the point, this point is C, this point is D. C and D, C and D represented as this Q1 is minus Ka d theta by dx, and Q2 at this point theta 2, this is here it is, this is Q1, this is Q2, the temperature theta, and here it is theta 2, theta 1, minus Ka, this is d theta by dx minus d2 theta by dx square delta x. Hence the amount of heat received, hence the amount of is given delta Q, that is Q1 minus Q2, is equal to minus Ka d theta by dx minus kx d theta by dx minus d2 theta by dx square del x. So this is minus Ka d theta by dx, this minus minus plus Ka d theta by dx plus d2, this Ka d2 theta by dx square into delta x. This is Ka, next page. It is delta Q is equal to Ka d2 theta by dx square into del x. This is the formulation. The rise in temperature of the material can be expressed as ms delta T, temperature, or delta theta. We take delta theta, rate of rise, is equal to m specific heat d theta by dt is equal to K A. We can write this m. M is mass. Mass is volume. A into delta x, that is volume, into density, mass, specific heat d theta by dt. So heat equation. What is heat equation? Loss due to radiation is equal to emissive power into area into temperature, excess temperature. That is E V into delta x theta. So equating the equations, that is Ka d2 theta by dt square del x is equal to A delta x rho c d theta by dt plus EB delta x theta. So Ka d2 theta by dx square is equal to A rho c d theta by dt plus EB theta. So this d theta by dt is equal to 1 upon A rho c. A rho c Ka into d2 theta by dx square minus EB theta upon A rho c. So we call this whole factor is small k d2 theta by dx square d theta by dt minus p. Then this is known as Fourier heat equation. This is known as Fourier heat equation. Fourier heat equation R R d theta by dt is equal to k d2 theta by dx square when p is equal to 0, no loss. So this is all about the heat equation. That heat equation we have to have this one case. So this is all about the Fourier transformation and its application along with the very interesting example. So these are a few examples that we have asked in the examinations. So we have tried it. There are so many examples in the book and you have to try all these examples. So